Okay, welcome to another video on applied electricity. So we are going to continue from where we stopped yesterday. So this is the solution for applied electricity first semester 2022-2023 academic year. Okay. So now let's get started. And when you get this video, after you've watched it, you will like and subscribe, and then you share it with your friend, because I'm sure most of your friends have also taken applied electricity, especially in UMath. Most of the engineering students, right, even those that are doing in petroleum department, and then also even environmental, right, and yes, as well as mathematics department, they are all doing applied electricity. So share this video with your friend. So if you know someone in first year, it's most likely that student has taken applied electricity this semester. So share with your friends so that they also get to benefit from the videos that I'm making on the solutions of the end of semester first semester examination on applied electricity. Okay, let's get started. Now, yesterday we stopped at question 60, so we are going to be solving another 60 questions, 30 questions. So we solve question 61 to 90. Okay, to 90. Now let's start with the first question of today, which is question 61. Question 61. If you look at question 61, a soft iron bar is introduced inside the current carrying solenoid, right? So you introduce this bar inside a current carrying solenoid, right? Now, the magnetic field inside the solenoid. So they want to know whether it's going to happen to the magnetic field inside the solenoid, right? So if you are through this, so this one, the magnetic field here is going to increase, right? And one way you can know that it's going to increase is because, right, if you have if you already have a current carrying solenoid, right, meaning it's a coil that is current is passing through. So if you are adding a soft iron battery, so that means that, let's say it's a coil. So I have a coil of this nature. This is question 61. So we have a coil, right? That's what we mean by solenoid. Solenoid is the same as a coil. So you have this current carrying, in this current here, let's say I. Now, if you introduce a soft iron bar to this, right, or just an iron inside it, that's what they mean. You place it. Let me use the French color. You place the iron here, right? This is our iron. Okay. So by doing this, you realize that here the magnetic field, when it comes to the magnetic field, right, the magnetic field here is going to increase, right? Because of what? Now you've introduced another material, which is iron. Remember, iron is also what? it's a magnetic material, right? It's a magnetic material. So by introducing an ion to this, the magnetic field, is going to increase. You have increase magnetic field. So the answer for this is going to be C, right? So question C is the answer for this. Now we go to question 62. An EMF of 16 volts is induced in a coil of inductance 4 henries. The change of current must be. So question 62, you can see that we are giving the EMF. Okay, I'm going to use E here to represent EMF, which is the value there is 16 volts. And then the inductance to L here is going to be 40 henries. So we have to find the change of current must be. So here we try and write the formula for the voltage across an inductor. Okay, so if you know the formula, that becomes easy. But if you don't know it, what is similar to what I've just wrote here, right? So if you have a coil, the voltage, as we know, or you can call it the induced EMF, we refer to this as induced EMF, will be equals to minus the inductance, then times the rate of change, the change of what? Current, right? Rate of change of current. Now, since the value for the EMF is 16 volts, it shows that we've taken the magnitude of the induced EMF. So let's take magnitude of induced EMF. So when you take the absolute value for this, so you realize that the induced EMF will now be positive. Inductance, rate of change of times the rate of change of time. Now you can see that from that we are giving the inductance and then the EMF. So we make the rate of change of current the subject. By doing so, we get rate of change to be equals to the magnitude of the EMF over the inductance. So we get 16 over the inductance, which is 4. We can just see here 16 divided by 4, that is going to give us what? 4. Remember the unit here is amps per second, rate of change. So the answer for this is what? D rather, right? So question 62, the answer is D. Now moving to question 63. Find the force acting on a conductor 3 meters long, carrying a current of 50 amps at right angles to a magnetic field having a flux density of 0.67 Tesla. Right? So here we are to find the force acting on the conductor. 3 meters long conductor. And then the current which is passing through the conductor is giving us 50 amps. And then the magnetic flux density is 0.67 Tesla. So based on this, we can write the formula for force that will be acting on the conductor inside the magnetic field. So if you have, the formula is this. So this one, you just have to remember the formula, equals to the magnetic flux density times current times the length, right? The length of the conductor times sine what? Theta, right? So this is the formula for this. And theta here, right, is the angle, right? The angle between the conductor and the magnetic field, right? So it's the angle between the conductor and the magnetic field. So we have been told here that angle is 180 degrees because the conductor, right, is at right angles to a magnetic field. So theta here is giving us 90 degrees. And as a result, we just write, and sine 90, when you put 90 here, sine 90 is 1. So we just get a simplified version to be magnetic flux times current times the length of the conductor. So we just replace the values. The force is now going to be magnetic flux density, which is 0.67 times 3, okay, times current first. The current is giving us 50, right? Then times the length, which is 3. Okay, so when you multiply this, that would give us the answer. So we have 6.67 times 50 times 3. So you get 100.5 newtons. So when we come here, the possible one, we have 100, A is 100, B is 400 newtons, C 600 newtons, and then D 1000 newtons. So the answer here will be A. That's the closest to the answer we got. Question 64. The magnetic flux through a coil is inversely proportional to A, magnetic field. The magnetic flux, no. Okay, if you have a magnetic field, the magnetic flux is actually directly proportional to the magnetic field. So let's say I have a charge. Let's say this is a positive charge, right? And there is a magnetic field around this, right? So I have a magnetic field here, meaning the area around the what? The charge. Now, when it comes to what? The magnetic flux, the magnetic are within the what? The area around the charge. Let's say this is a positive charge. So the magnetic flux, which is phi, is that proportional to the magnetic field, right? So actually, when we say magnetic field, we are actually talking about the magnetic flux. So A here is actually so it's actually wrong. Then B, the number of turns. So here, if you have a coil, like we have indicated earlier, this example. So if you have a coil, then the number of turns in this coil, again, that will also be that proportional to the one, to the magnetic flux. Because if you are having just one single coil, let's say of this, right? Single coil of this, right? and then you compare to one whereby you are having a lot of coil. So this one here, the magnetic flux here is going to be more. Okay, so the second part here, which is B, is also wrong. Is directly proportional to the magnetic flux, right? The number of turns is directly proportional to the magnetic flux. Now C, the area here, if you can, the formula for magnetic flux density, which is D, right, is equals to what? Magnetic flux over area. So if you make magnetic flux a subject, you get magnetic flux density times area. You can see that the magnetic flux density here, which is V, is directly proportional to the area that we have here. These two are directly proportional. So you can see that C2 is also wrong. So the answer here becomes D, right? Because none of them are. So none of this is inversely proportional to the magnetic flux. So here is D. Now let's go to question 65. Magnetic flux is linked with a coil when a current of 2 amps flows through it. What is the self-inductance? So this question is actually incomplete. Okay, question 65 here is incomplete because we don't know the distance. We are just being given the current, right? We don't know the the flux, the change of flux. You don't know any other parameter. So question 65 here is incomplete. Okay, so I think it was given as a bonus. Okay, now moving to question 66. The area of a hysteresis loop varies with the type of material, true or false. So here, if you have an hysteresis loop, so yesterday we looked at an hysteresis loop, right? The area varies with the type of material. Yes. So depending on the type of magnetic material you have, the area is going to be different, right? So that's why we can even classify magnetic materials into two groups. We have soft ferromagnetic material and hard ferromagnetic materials, right? It is because of what the area of the hysteresis loop, right? I mean the hysteresis loop that you have, it depends on what, it varies with what, the type of material. So the answer here is true. Okay, so different materials are going to have different hysteresis loop. A current carrying conductor, that's question 67. A current carrying conductor is moving toward the viewer. What is the direction of the force acting on the conductor, right? So here to find here the direction of the force, right? The direction of the force acting on the. Okay, so with this question here, I think here it should be the direction of the. It should be the direction of the magnetic field, right? So there is a problem with this question, question 67. It should be the direction of the magnetic field. Why? Because here we are the force. When we talk about force acting on the conductor, it can only be upward or downward, right? So if you look at the possible answers, we are having question A anti-clockwise, B towards the viewer, C away from the viewer, and then D clockwise. Right? So this one has to do with what? The direction. So it's with the direction of the magnetic field in the conductor. So if you are having a current carrying conductor, right? Because it's just a current carrying conductor, it's not even inside the magnetic field. So there's not going to be any force acting on it. So we just have talking about a current carrying conductor. So this part here should be the direction of magnetic field. Right? Direction. Okay, let me. This will be direction of magnetic field. Okay, magnetic field. So if you are having a current carrying conductor, right? And we have been told that current is what? So meaning the current here is moving towards the viewer, right? So with this we can use the grip rule, right? Grip rule. Especially we can use the left hand grip rule, right? So if it's moving away from it's moving towards the viewer, right? This is moving towards the viewer. So in that case, we know that if it was moving away, right, and you are using your left hand, right, so meaning you are trying to use a left hand grip rule, the direction of the magnetic field will be what? Will be clockwise, right? So if it's moving towards the viewer, meaning it's going to now be the opposite. So here, the answer here is supposed to be what? A, right? Anti-clockwise. So if you are using the left hand grip rule, if the current is towards the viewer, here the direction of the magnetic field should be anti-clockwise. So we move to question 68. If a conductor is moved back and forth, right, at a constant rate in a constant magnetic field, the voltage induced the conductor will be, right? Okay, so if you have a conductor if a conductor is moved back and forth at a constant rate in a constant magnetic field, the voltage induced in the conductor will be A, remain constant, right? Then B, reverse polarity, B, reduce, and then D, B, increase. So here, right, if you look at the positive answer, so if I'm moving a conductor back and forth, right, so if you are moving first forward, right, that means the voltage will be what? Positive. When you now move back again, right, then you are getting negative, right? So here you'll be having positive and negative, right, back and forth. So here the induced voltage is supposed to be reverse polarity, right? So the answer for this is supposed to be B, right? B. Now question 69. We have question 69 here. The flux density produced in an iron ring of relative permeability 1600 if it is wound with a coil which produces a magnetic field strength of 500 amps per meter is given approximately as. So here we are to find the flux density, right? Because we say the flux density, right? So what is going to be the flux density? If this thing, you have an iron ring of relative permeability 1600. Relative permeability here of the iron here is giving us 1600. And then so this ring is wound with a coil which produces a magnetic field strength of what? 500 amps per meter. So we have here H, right? H here represents magnetic field strength. So we have 500 amps per meter here. Now we have to find the magnetic flux density, which is yes, right? We have to find the magnetic flux density. Okay. Now, to solve for the magnetic flux density, right? I think here, let me come here, it's supposed to be B, right? I think this one's supposed to be B. The symbol for magnetic flux density is, we use letter B, right? Okay. So that when we come here, this time magnetic flux density B here over the magnetic field strength so be equals to what? The absolute permeability of the material, meaning of what? Iron here. The material is what? Iron ring, right? So it should be this iron ring. Right? Now the absolute permeability of iron ring is going to what? The relative permeability of the iron ring, right? Times the permeability of what? Free space, right? Permeability of free space. So with this, you can see that we now have a formula which is B over H will be equals to the relative permeability of iron times the permeability of what? Free space. So we are interested in what? The magnetic flux density. So we are making here be the subject so that we get this formula, right? H. So this means I'm just replacing the formula straightforward. The relative permeability is giving us 1600. Then the permeability of free space is a constant value, right? And then is equals to 4 pi times 10 to the power minus 7. So you have to know this, right? Permeability of free space is equals to 4 pi times 10 to the power minus 7. Okay. This is a constant value. Right? So when you come here, you come and replace. Now let what? Multiply by the magnetic field strength, which is giving us 500. So we just use our calculator to do the calculation. So here I'm going to have we are going to have 1600 times 500 times 4 times pi times 10 to the power minus 7. Okay. So when you do all, you get what? 1.05, right, Tesla. So you get 1.001 Tesla. So the answer here will be what? A. So when you do this, you get 1.005 Tesla. So the answer for this is A. Now moving to question 70. Question 70. Which of the following statements is false? the inductance of an inductor increases. So here it's talking about the inductance of an inductor. An inductor is simply a coil, right? It's simply a coil. I sketched this just even today, right? So you have a coil of this nature. Right? So we tend to even have air core, and then we have iron core, right? Iron core inductor. So we have this kind of inductors. So if you add, now we are talking about interested in the inductance, right? So the inductance of an inductor. So you have to write this formula. The formula inductance in terms of what? The number of turns. So we have n squared is equals to what? The absolute permeability times area over what? The length, right? Of what? The listen exposed in the magnetic field. So we have this formula. This is a formula for inductance of an inductor. If you look at this formula, this is a formula that we are going to be using to answer question 70, right? Question 70. Which of the following statements is false? So we are looking at the statement which is going to be false. The inductance of an inductor increases A, with a short, thick coil. What we mean by a short, thick coil, meaning here, if you have a wire that is what? Let's say it's long, right? We are looking at ways we can increase the inductance. So if you have a short, you see that the length here, which is L, is inversely proportional to the inductance. So if you are increasing the length of it, you can see the inductance will decrease. So that means if I want to increase the inductance, right, I want this to increase, I have to decrease the length, right? So if you are having a short, right, short here is talking about this part here, the length that is exposed in the magnetic field. So if you have a short, it's going to increase the inductance. And then thick coil. Thick here is talking about the wire that we have. So if you have a thick coil, meaning the area, right, the area is going to also be what? It's going to be larger, right, than if you have a very thin coil. So then the area here, you can see directly proportional to the inductance. So if you are increasing the area by making the coil thick, then the inductance will also increase. So you can see that the first part here, A, is correct, right? So that part is correct. Now let's go to B. When wound on an iron core. So if you have a coil now, you decide to insert iron core inside it. So that's what we refer to as what? An iron core. If you look at the formula that here is a absolute permeability. Absolute permeability is what? Relative permeability, let's say, of iron times the permeability of free space. So you can see that by introducing the what? Iron, you see that the formula now becomes right. So you see the formula now is that because of now you are introducing iron, you are now going to get a high inductance. So when one on an iron core is what? Is also going to increase the inductance. C, as the number of turns increase. So you can see the number of turns, which is N, is actually proportional to the inductance. So increasing the number of turns, meaning you are increasing the inductance. So C2 is correct. D, as the cross-sectional area of the coil decrease. So when we talk about cross-sectional area, which is just the area of the coil we are talking about, if you are decreasing the area, right, you can see that the inductance too is going to also decrease because that proportional, they are directly proportional to each other. So the answer here is D. That's a false one. D. Now question 17. Flux in a magnetic circuit can be compared with an electric circuit too. Okay. So here we are looking at analogies, right? So let's say current. We know that the current is inversely proportional to voltage supply. And when it comes to flux, right, it's also inversely proportional to to the magnetization force, right, or the magnetomotive force, right? So you can see that with this, you can get Ohm's law to be the voltage over resistance, and then with this you also get the Fm over S. S here is also the reluctance. So here the flux is can be compared. When we are doing comparison, flux can be compared to to current, right? It's similar to current when we are now talking about magnetic circuit. So we have here to be B. Okay, so 71 is B. The term permeability means, here when we talk about permeability, we are looking at how easily, right, magnetic field can be established on a material, right? So if it is easier to establish magnetic field on a material, that means we say the permeability is high, right? It's high. But if it's difficult, right, to establish magnetic field on a material, we say the permeability is low. For example, if you are having iron, right, which is similar to a nail, right? If you have a nail and you rub it against a bar magnet, you can see that it's become magnetized easily. But if you are using a glass and you are rubbing against a bar magnet, it's difficult, right, for you to establish magnetic field on the glass. So it's the same concept here. So the term permeability means, so we are looking at which of these statements is going to be true when we are talking about permeability of a material. So the term permeability means A, the number of turns on an air core. No, that's not a definition. B, the amount of reluctance of 1 cubic centimeter of air. No. C, mmf required to produce 1 unit of magnetic flux. That is wrong. And then D, the ability of a substance to conduct the magnetic field lines of force. So is what I talk about. So here is the same definition, right? But there is being framed in a different way. So the ability of a substance to conduct the magnetic lines of force. What that means is the ability of the material, right, to able to establish on it, right, or to conduct magnetic field, which is the same magnetic field, magnetic lines of force. We are referring to magnetic field. Okay, so magnetic field. So the answer here for 71, for 72 rather, is going to be D. Now question 73. Current flow in a straight conductor produces current flow in a straight conductor produces A, permeability. No, permeability. Okay. B, hysteresis. C, a north pole. D, a magnetizing line of force. So the answer here is D. If you can remember the formula for magnetization force, right? Because if you have a material, like in this case, you are having a conductor, you pass current through it. We know that there's going to be a magnetic field. Let's say I have a conductor and there's current passing through this. There's going to be a magnetic field, right, around this, right, or on this material, right? Maybe you have magnetic field around this. This is just rough lesson. Now, this magnetic field that is around the conductor, we say is because it's due to what? Fm, right? The magnetization force, right? The magnetization force or magnetic lines of force. Right? So if you have current flowing through, so you are going to have magnetic field, magnetic lines of force, meaning magnetic field around the conductor. That's what this is referring to. So the answer for this is going to be D. Yeah. Question 74. The ability of a substance to retain its magnetism after the magnetizing force is removed is, here is what? Retentivity. We saw similar question yesterday. So the answer here is retentivity. If you are having a material, right? For example, you rub, again, you take a look at what? A nail. You rub a nail against a bar magnet, right? After you remove the nail, right? Meaning that time you are now making the magnetizing force to be 0, right? So you can see that once you remove it, the magnetism in the nail will maintain for some time, right? It's going to stay in the nail for some time before it disappears. So that is the amount that of time is going to stay, is what we refer to as retentivity, right? So the answer for this is going to be D. We refer to that as retentivity. That will be the ability of a substance to retain its magnetism after the magnetizing force is removed. The question 75, the equivalent to Ohm's law for a magnetic circuit is Ohm's law. I just wrote this, right? You see that Ohm's law, we say that the current is directly proportional to the voltage supply, right? And then when it comes to what? Magnetic circuit, we say the magnetic flux is directly proportional to the what? The magnetomotive force, the magnetization force, Fm, right? Fm. So you can see because of that, current is equal to the voltage supply over resistance, and then magnetic flux is what? Fm over what? The reluctance, right? So here, Ohm's law for magnetic is going to be what? MMF. Fm is the same as what? MMF. MMF, meaning magnetomotive force. So the answer here is going to be what? B, right? It's going to be flux equals to MMF over reluctance. So reluctance here, I'm using what? S. S here stands for reluctance. Right? Reluctance. Now, moving to question 75. If a coil has 250 turns and carries a current of 5 amps, then the MMF is, so here, if you have this in a coil, and then you know the number of turns and the current which is passing through. So it's similar to what I wrote earlier. So it's just like here, for example, now, let's say you have current passing through this I, okay? And now the number of turns here, which is N. So Fm, or the magnetization force, or MMF, is going to be equals to the current times what? The number of turns. So this is just going to be current, which is 5 times 2, 50. So when you do the multiplication, this will be 0. 5 times 25, that will be 125. So the answer here is A, which is 1250 arms 10. Now moving to question 77. An iron is used in power transformers in order to, right? So if I'm using iron in a in a power transformer, what is going to be the use for it? A, reduce the resistance of the coil. No, when you are having an iron, we saw that in an iron core inductor, right? You are going to have the reluctance is going to increase, right? Because you are now having iron, which is a magnetic material. So we have B, reduce loss in the core. No, because now with the iron there isn't going to what hysteresis, right? And hysteresis is a form of energy which is associated with what? A magnetic material, and that energy is being lost in the form of heat, right? So B here is incorrect. C, reduce the magnetizing current of what? The transformer, right? So here, and then D, none of these. So here they reduce the magnetizing force, magnetizing current of the transformer. That is going to be the answer. So the answer here will be what? C, right? The answer here will be C. Because you can look at it, you can think of it in terms of even so you can think about this in terms of reluctance, right? And then the current which is passing through the iron core, right? So by intro it will reduce, because now, because of what? With the iron, you are now going to have reluctance, meaning resistance, right? So that resistance is going to oppose the flow of current, right? So if you are having now the iron is a conductor, you've introduced it, so you are going to now, the current is going to what? It opposes the current. So by inserting the iron, you are going to reduce the magnetizing current. So the answer here is C, right? Because of the resistance of what? The iron. Okay. 78. The property of a material which opposes the production of magnetic flux in it is known as reluctance. We refer to that as reluctance, right? So if you have a material and you are trying to establish magnetic field, which is the same as magnetic flux on it, the opposition of that material to the establishment or production of magnetic field or magnetic flux is what referred to as reluctance. The conductance of an electric circuit is analogous to, here question 79. We even saw this, right? We solved this the last time, right? This one is going to be the conductance of an is going to be analogous to be permeance. Remember I said the answer. So this question is a repeated question, right? The answer was permeance, so it's the same thing here. Question 80. A magnetic circuit requires 800 amps 10 to produce a certain quantity of flux in a magnetic circuit, right? This is question 80. If its excitation coil has 100 turns and 5 ohms resistor, the voltage to be applied in exciting coil is, okay. This question here if you look at what we are given. So you focus on what you are given from the question. That will allow you to solve for this. So we have been so a magnetic circuit requires 800 amps turn. So if you look at amps turn here, you see amps turn is a unit of what? FM, meaning the magnetization force, or MMF. So FM here is giving us 800 amps turn, right? Now, so this will produce a certain quantity of flux in a magnetic circuit if its excitation coil has 100 turns. So meaning N, the number of turns here, N is 100. Okay. Now, and then a 5 ohms resistor, the voltage to be supplied in exciting coil. So we are now interested in the voltage. So if you look at what we are giving, we are also giving what? Resistance to be 5 ohms here. So if you look well, if I have resistance and we are interested in voltage, right? We know voltage is what? Current times what? Resistance. So how do I find our current? You can see that you can find current by using the same formula that we wrote earlier. This formula. Then we make current the subject. So you see that current will be equals what? Fm over number of turns. And then Fm here is 800 divided by number of turns, 100. So you see that we get 8 amps, right? 8 amps. Now we come and replace this in the voltage formula. So we just have current is now 8. So 8 times what? 5. That's going to give us 40 volts. So you see that the answer here for question 80 is what? 40 volts. So we get the answer here to be C. Now moving on to question, right? To the next question that we have. We have question 81. In all cases of electromagnetic induction, an induced voltage will cause a current to flow in a closed circuit in such a direction that the magnetic field which is caused by the current would oppose the change that produces the current. Is the original statement of. So here they are just talking about a law, right? So which law is this talking about? And the question, the answer here is going to be Lenz's law, right? Lenz's law is just saying that if you have a coil, right? Again, you have a coil, right? And then you have the rate of current that is flowing through the coil, right? And due to that, as a result, you get an induced EMF in the coil, right? Which we refer to as minus inductance and rate of change of current. Now, with this, right, that's where the negative here comes from. What that means that at a certain point in time, this thing will start to oppose, right? The coil will start to oppose the induced EMF, right? And that the current will oppose the change that produced. So now you now have induced EMF, which is what going to be negative. And this is the law of what Lenz's, right? So that's why we always indicate this one here, right? So that's Lenz's law. Any material that is difficult to magnetize has. So if you have a material and it's difficult to magnetize, meaning the material is having a low permeability, right? Remember the definition of permeability is how easily magnetic field can be established in a material, meaning how easily you can magnetize a material. So if it's easier to magnetize the material, meaning the permeability is high. If it is difficult, then the permeability of that material is low. So the answer for this is what? D. Okay, D. So if it's difficult to magnetize the material, it is having a low permeability. So for example, glass is having a low permeability. Question 83. A coil of 1000 turns is wound on a core. A current of 2 amps flowing through the coil creates a core flux 2 milliwebers. The energy stored in the magnetic field is, so here you have to find the energy stored in the magnetic field. And then to solve this, meaning now you can just start by writing the formula for energy stored in an inductor, because we are talking about a coil. A coil is just the same as an inductor. So question 83. So the energy stored in an inductor is going to be equals to half the inductance times what? The current square, right? Current square. So if you go back and look at question, right, 83, you can see that we are given the number of turns. We have 1000 turns, right? N is 1000 turns. And then we have been told the current here, I, is 2 amps. And then the flux is 2 milliwebers. Okay. So you can see that with this, we are not giving inductance. But if you look at our formula, we have inductance here. So we have to find a way to calculate inductance and then replace it in the formula. And then, so for this inductance, the formula for inductance, we know is going to be equals to the number of turns times the rate of change of what? Current over the rate of change of what? Over the change of current over the change of what? Flux. So you can simplify this to just mean current over what? Yeah, this thing over what? Flux. So this will just give us, we know the current, we are just going to replace the number of turns. We have 1000, right? Times the current is 2, then divided by this thing, right? Divided by the flux. And the flux, or is the other, I think the formula, probably wrote this formula wrong. Okay, the formula for this is rather the other way. I don't know. I think it's a change of flux. Okay, just a minute. Formula here is a change of what? Flux rather over current. So this becomes, right? This is going to be flux over what? Current. So here we're supposed to have, here is supposed to be what? The flux, which is 2 milli, that is 2 times 10 to the power minus 3 over current, which is 2 amps. So the inductance will be equals to, you can see 2 here will cancel this as 3, so it will cancel this. So we get 1, right? 1 Henry for the inductance. Now we go and get the energy. So I'm going to have half the inductance, which is 1, times current, which is 2, square of that. So that will be what? 4 divided by 2. That will give us 2 joules, right? So the answer for question, this was 83, is going to be D, right? 2 joules of what energy? 2 joules of energy. Now we move on to question 84. Energy stored by a coil is doubled when its current is increased by, okay. So this question is similar to the one we solved yesterday, right? It's about doubling again or reducing. Here again we make use of the what? Proportionality, directly proportionality and inversely proportionality. So if we are having the energy, just like the formula we wrote earlier, you can see that the energy here is directly proportional to the what? Here we are talking about energy and then current, right? That proportional to the square of the current. So I can write here to the square of what? The current. So we have been told that the energy stored by a coil is doubled. So meaning the first case we have this. Now let's say if you were to double this, right? The energy. What is going to happen to the current? That's what we are supposed to find out. Now if you look at this, I can make it what? Okay. In a way, we can try and make current the subject, right? With this. So that I have current that's proportional to what? To E. So if we're to what? Square both. So we can see that current here will be what? That's proportional to the square root, right? You square both sides so that this will go away. Square root of what? E. Okay. So this will be the relation between the two. So that means that now if you were to double, so let's say you were to double now the energy, so that means the current, maybe let's put here I1 and then E2. Let's say now E2 is being doubled, meaning twice of what? E1. So you can see now E2 is going to be that proportional to what? A square root of what? E2, right? So when you place the one, which implies E2 will be equals to what? Root 2 E1. So you have this, okay? You have this. So by doing this, you can see now we have, if you double the energy, that means that you are now going to have square root of what? Meaning root of what? 2, square root of 2 times what? The energy. That's what this means. So based on this, we can now write, or maybe you can just even make this root 2 here times maybe E1, right? So you get this kind of question. So what this simply means, now if we are now interested in the percentage, right, you can see the answers are given in percentage. So what this means, I can write, if it's percentage, I can now take I1 over what? I2. My I1 here, the proportional in terms of what? The energy is what? Root. Sorry, it should be what? I2. The out mean the second lesson. Yes, will be I2. Okay. The second current over the first current times 100. So which is root 2 E1 over here is what? Root E1. So you can see that by doing this, root 2 here is the same as E1 over root E1. So with this, we are going to get this will cancel. So I have root 2 here. Once I have this, then you multiply by 100, right? Because it's percentage. Because this will multiply by 100. Okay. So that's just meaning root 2 here times 100. Root 2 times 100. That is going to 104 to 1. So the answer here is C. Okay. So we get here to 141.42%. Okay, this is percentage. Question 85. The flux density produced in an iron ring of relative permeability 1600 if it is uniformly wound with a coil which produces a magnetic field strength of 1000 amps per meter is approximately 2. I think this is similar to the same question we solved earlier, right? So here again we are interested in the magnetic flux density. So again, the formula here, so I'm not going to write the formula. We already wrote this formula. It's somewhere here. Okay, this is the formula we wrote. So it's the same formula, right? So the same formula here. So this question here, meaning let me just write it here. Question 85. So this question again is the same formula. You can see that you are being asked to find the magnetic flux density. You are given the permeability. You are given the magnetic field strength. So it's the same formula here. So I'll just write in this. Now have 1600 times what? Permeability of free space times 4 pi times 10 to the power minus 7. Now times what? Here is now 1000. So you can even, we know here was 1, right? 1000. So we know 500, we what? 5 times 2 will give us what? 1000. So meaning we can even just simplify this. So this just be 2 times what? The answer we got, which was 1. So here's will be what? 2.0, let's say 001, right? Tesla. So the answer here will just be 2. Okay. So we get question 85. 85 will be 2 Tesla. Now question 86. Thus found that the potential difference across the ends of many conductors is directly proportional to the current flowing through them, provided temperature remains constant. So here we are talking about who stated this law, right? The fact that the potential difference referring to the voltage supply, right, is directly proportional to a conductor. So you can see that is what? Ohms. And the full name is what? George Simon Ohms, right? So it's what? B. Question 87. A current in a circuit is due to the potential difference of 10 volts applied to a resistor of resistance 100 ohms. What resistance will permit the same current to flow if the current supply voltage, or if the supply voltage were 1000 volts? So here we have question 87. Okay, now we are being told that a current in a circuit is due to a potential difference of 10 volts applied to a resistor of what? So let's start with what? The voltage here, 10 volts. Then the resistance R is 100 ohms. What resistance will permit the same current to flow to flow if the supply voltage were 1000 volt. Okay, so this question is just saying, so the first case, you can see that we are giving the voltage and the resistance. So you can find the current, which is going to be voltage over the resistance. So you get 10 divided by 100. That will give us 0.1, right? Ampere. So we have 0.1. Now, if this current, meaning the same current is now, meaning now we have 0.1 amps here, was to what? Pass through or flow through what? The resistor, right? Was to pass through a resistor. So meaning we are interested in what resistance, right, will permit the same current, meaning if this current passing through, if the voltage supply is now 1000, right? So meaning now we are maintaining the current to be 0.1. Now we are now finding the resistance, and then in terms of the voltage here. So you make this resistance a subject here, that will become voltage over current, right? So now I'm having the voltage supply to be what? 1000 divided by the current, which is what? 0.1. So that is going to give me 1000 times 1, right? This one you bring up. So you get 10,000, right? That is just 10 kilo ohms. So if you look at the answers, they are expressed in kilos. So that will be C, 10 kilo ohms. So question 87 is C. Question 88. A voltage divider is to give an output voltage of 10 volts from an input voltage of 30 volts, as shown in the figure. Given that R2 is 1 kilo ohms, calculate the resistance of what? R1. So if we look at this question, right, we are interested in the resistance here of R1. So it's a voltage divider. What that means that the resistors here, they are connected in series. What that means, the resistors that we have here, they are being connected in series, right? R1 and R2, they are in series. So the same current will pass through this, right? So we look at here. Look, if you look where you can see the voltage across. So let's say this is V2 across the what? R2 here. You can see the answer here is what? 10 volts. And then the resistance from the question, given that R2 is 1 kilo ohms, so meaning R2 is 1 kilo, which is 1000 ohms. Now calculate the resistance. So we are interested in finding the resistance of this. So to find the resistance, you can see that when you come to V2 and R2, I know the voltage and the resistance. So I can calculate the current. So again, the same Ohm's law, current here with V2 over what? R2. And that will be 10 divided by 1000. So this will be what? Okay, 10 raised power minus 2, let's say amps. Right? Get 10 raised power minus 2 amps. Now, we look at now we are interested in the resistance, right? So this answer we got here, which is 10 raised power minus 2 amps here, that will be the current, right? Because it's the same current that will pass through this. Mean the current that is passing through this here, right, is actually 10 raised power minus 2 amps. So that's the same because they are in series. So if I'm interested in finding the resistance R1 here, once I know the current, I know that R1 here, because in terms of the voltage across this, R1 is going to what? V1, meaning I can write R1 will be equal to what? V1 over what? I1, right? But now I don't know the voltage of V1, but we know the current. So to get the voltage with this, you can see that we can use what? Kirchhoff's voltage law here, right? Because if we have a circuit diagram, we can move what? We have one loop here, and then we can move, let's say, clockwise. And by doing that, we apply Kirchhoff voltage law. So you can see here we have 30. Now I'm going to indicate the polarities on the resistors. So here the current is moving down, so I'll indicate here plus, minus here. Another, the same current, which is what? Plus here, minus. So I've indicated the polarity, meaning the Kirchhoff voltage here will be what? 30 here is going to be rise, right? So we have 30 minus, let's say V1 minus V2, right? V1 will be drop, right? Because we have positive to negative here to positive, so we have drop. V1 and V, they are both drop, so you get this to be equals to 0. Now, from the question, we know what? We are given V2, which is 10 volts. So you can see that I can make V1 the subject. V1 will now equals to what? 30 minus V2, which is 30 minus 10. That's going to give me 20 volts. Once I've gotten the 20 volts, I can now come and calculate R1, the resistance. That is for V1. This is V1. That's giving me this. So this is going to be V1, which is now 20 divided by current, which is 10 to the power minus 2. Right. So when you bring this up, that will be 10 to the power positive 2. So that is going to what? 2000. Right? So you get to be 2000 ohms, which is the same as 2 kilo ohms. So that will be B here. So the answer for this is B. Wow. This one is taking much time than I expected. Then we look at the last question, which is question. Okay, the last two questions. We have question 89. Okay, yeah, 89. What is the charge transfer in a period of 8 seconds by a current flowing at the rate of what? 2.5 amps. Okay, so we have current, and then we are interested in the charge. So we are given the period, right? So meaning time here, you can say it 8 seconds. The current is giving us 2.5 amps. Here we are interested in the charge. We know that current is the flow of charges, meaning you have charge over time, the rate of flow of charges. And then we are interested in charge, so we make charge and so we get current times time. This is going to now be, the current is 2.5, time here is 8. So 2.5 times 8 times 8, that is going to give us 20 coulombs, right? So we get 20 coulombs. So the answer here is C. Then question 90. The algebraic sum of voltages around any closed path in a network according to Kirchhoff's voltage law is equals to. So if we were to do the algebraic sum, like we just even wrote here, right? The algebraic sums will give you 0 if you have a closed circuit, right? So when you can, that is what? 0. So we have here the answer to be C. Okay, so that's the end of today's video. So we continue tomorrow. Bye bye.